Neutral Atom Renewable Energy Forecasting, or NAREF for short, is our proposal to harness Pascal's neutral atom quantum computer for renewable energy forecasting. To reduce CO2 emissions, we must move to more renewable energy sources. However, renewable energy production depends on highly complex, chaotic weather conditions, making forecasting extremely difficult. A 1% forecasting error in 1 hour can lead to 8.5 tons of CO2 emissions that could have been prevented with a more accurate model. Some deep learning models that can predict the behavior of such complex systems can be hard to train and require a great amount of energy and data. Many such models require access to high performance computers, thus overriding the CO2 advantage. To reduce the energy cost of accurate forecasting models, we propose to use reservoir computing. Reservoir computing is a machine learning framework that is very low in energy consumption. A reservoir is a physical system with complex dynamics, such as a quantum system, and is used to reproduce the dynamical behavior of the renewable energy source. A good reservoir should have highly complex dynamics that are easily adapted to different problems. With its reconfigurable atom layout and analog framework, Pascal's device presents an ideal candidate for a quantum reservoir. In our proposal, we encode the input data in the amplitude of a pulse and let the system evolve before injecting the next input with another pulse. We repeat this process for subsections of the input data and measure the reservoir state after each subsection has been seen by the quantum system. At the end, a simple linear regression is performed, which makes reservoir computing extremely energy and time efficient. The dynamics of the system are influenced by the atom layout. We implicitly encode the temporal dependencies of the data in the interactions between the atoms. We conducted an extensive hyperparameter search to find the ideal atom layout to perform complex time series forecasting tasks. Our so-constructed quantum reservoir was able to predict the behavior of the chaotic Mackey-Glass time series with only 1.2% error, using only 250 training points and 9 atoms. We could not find any classical reservoir configuration that was able to achieve a similar result without significantly increasing the number of training data. This result suggests that the dynamics of the quantum reservoir are able to easily reproduce the behavior of chaotic systems, such as those of renewable energy sources, with significantly less data than a classical reservoir. While classical reservoirs are already very low in energy cost, their performance does not scale well enough to be applicable in industrial use cases. As we have demonstrated in our simulations, our quantum reservoir is able to more easily adapt to complex tasks with less data. As the data becomes more complex, we expect that our quantum reservoir will be able to rival the performance of deep learning models without the excessive cost in energy and reducing CO2 emissions by a factor of 10. Combining our algorithm proposal with Pascal's neutral atom quantum computer, we hope to contribute to a more sustainable future.